So this is the last section, chapter 12. Again, we're not going to deal with anything other than the homework assignments this semester. Everything else, quiz and activity and test and all that stuff for chapter 12 will happen next semester. Last time we talked about the binomial distribution as an example of a discrete distribution. Here we're going to be talking about the normal distribution as an example of a continuous distribution. So the graph, since a normal curve or normal probability density function, or a normal distribution, gosh, that's what I'm searching for, is continuous, we can graph it with a smooth curve. Right? That curve is called a density curve. And it has a couple of properties. It's always above the x-axis, and it has area of 1 underneath it. That area under the curve is going to represent a probability. So an example of a probability density curve. So here's a histogram of the scores of some 7th graders for some part of a test. I can model that histogram with a smooth curve. If the area under that curve is 1, then we'd consider that a probability density curve. So if we talk about measures of center and spread, like we went back all the way back to like chapter 3 or whatever when we talked about this stuff. So reminder that one measure of center is the median. So that's going to be the value on the x-axis that divides that probability curve into equal areas. The mean is the balance point. So if the curve was made out of like a solid and you wanted to try to balance it, that would be the spot where it balances. Now, in the case that our curve is symmetric, the median and mean will be at the same location. So, for example, if our density curve looks like this, my median and mean are in the same location right here. If it's skewed, we remember from earlier that the mean is pulled towards the skew more strongly than the median. So if we want to talk about spread, typically we're going to use standard deviation. One particular important group of these probability curves is the normal distribution. All normal distributions are symmetric. They all have a single peak. So they have a single median or mean. And they are all what is called like bell-shaped. So I can describe any normal curve by just stating its mean and its standard deviation. So the way we write a normal distribution is we say our random variable x is related to, and we use the capital letter N for normal, and then we list the mean and the variance, right? The standard deviation squared. So normal distributions are quite useful. They give good descriptions of real data and good approximations of, like chance outcomes. So important rule for normal distributions is what's called the 68, 95, 99 rule. So that says that 68% of the area under the normal curve is within one standard deviation of the mean. So if the mean here is at 0, one standard deviation away from the mean means 68% of the data is covered there. 95% of the data is within 2 standard deviations of the mean. And 99.7% of the data is within 3 standard deviations of the mean. This is a super important relationship to have to remember. We'll use this a lot in solving problems. So suppose we have the following 3 normal distributions. So we have mean of 5 and a standard deviation of 2. We have one with a mean of 10 and a standard deviation of 2, and one with a mean of 15 and a standard deviation of 2. This is what they would look like. What do you notice about these 3 normal curves? They're the exact same shape. They've just been shifted, right? So notice when the mean is 5, it's centered at 5. When the mean is 10, it's centered at 10. When the mean is 15, it's centered at 15. And kind of the height and width of the curve is going to be dictated by that standard deviation number. So if the standard deviations are all the same, like the height and width of the curve, the shape are all identical. But if the means are different, that means the location of the curve would be different. Now let's look at a situation where the mean is the same and then the standard deviation is the difference. So here, each of these 3 normal distributions has mean of 5, and the standard deviations are 1, 2, and 3. So if I look at the standard deviation of 1, I have a tall and skinny curve. Standard deviation of 2, it's a little bit shorter and wider. Oops. And a standard deviation of 3 is the shortest and widest of the 3. So the takeaway here is the shape of the curve is dictated by the standard deviation. The bigger the standard deviation, the shorter and wider the curve is going to look. Everybody's okay? So let's relate this now back to probability, since that's what we've been talking about for the most part. So let's say we asked a group of students to pick any number between -10 and +10. And then suppose we found the choice of the number was a normal distribution. So here's our normal distribution representing that. If I wanted to figure out the probability that some student selected a number less than 5, or more formally, the probability that x is less than 5, I could do this by simply finding the area under the curve that is below 5. Now, when we say simply, it's not so simple of a procedure. It actually requires like techniques in calculus that we don't have. But you know what we do have? Graphing calculator. You know what the graphing calculator can do? Can do that computation for us. So that's what we'll end up doing. But that's the idea here. And so looking at the probability that x is less than 5 is simply this area under the curve, will be an important conceptual piece in doing problems in our homework. Now, you won't be calculating the area directly, but it's conceptually, it's an important piece to have. So one thing to note, because this curve is continuous, the probability for any normal distribution when x is a fixed value, when x is just equal to 5, is 0. So in a continuous distribution, the probability of x taking on a single value is 0. So the important takeaway for you is, in a continuous distribution, there's no difference between the probability that x is less than 5 and the probability that x is less than or equal to 5. So if we think about it again as the probability of being area under the curve, if I have just one number, the area or the drawing under the curve is just going to be a straight line that has no area, right? If you think back to geometry, a straight line has no area to it because it's a one-dimensional figure. Hence why the probability when x is equal to 0, or x is equal to a fixed value is 0 in a continuous distribution. So if I have the probability that x is between -5 and +5, that is going to be the same probability whether we include -2, or it includes 5, or it includes both -2 and 5. Same probability. So I want to go back and talk about percentile rank. This was something we did early on in the semester. So if you remember, the pth percentile is the of a distribution is the value with p% of the observations less than it. So remember, we did problems like this. Like we said, okay, Jenny earned a score of 86 on her test. How did she perform relative to the class? Like, what is her percentile rank? So I'll count up how many scores I had total, which was 25, and count out the number of scores that were strictly less than 26 or 86. And I found there are 21 of them. 21 out of 25 is 84%, so she's in the 84th percentile. Now, we'll do that same kind of thing with a probability curve here later, because notice that the percent of scores less than 86 would be the probability that p is, or probability that x is less than 86, right? So we'll also do the same type of problem with a, like a probability function later. Next thing I want to do is talk about this idea of the standard normal distribution. So let's say that you're taking a math class and Mr. Kulik is your teacher, and your friend is taking the same math class, but Miss Garcia is his teacher. You guys both take the same chapter test. You got an 85 and your friend got an 83, and you ask, okay, who really did better? Well, what if the mean in his class was, different than the mean in your class? You should be compared relative to your class rather than just score alone. So what we do is create something called a z-score, which kind of standardizes your scores relative to the mean and standard deviation. So that's what we're doing. So we say that if x is an observation from a distribution that has a known mean and standard deviation, the standardized score, or z-score, of x is x minus the observation minus the mean divided by the standard deviation. That's called a z-score. If you do that to every value in a normal distribution, what you get is called a standard normal distribution. Every standard normal distribution is going to have a mean equal to 1 and a standard deviation equal to 1. I'm sorry, mean equal to 0, right? Because if I take mean and subtract the mean from it, I get 0, right? And if I take everything and divide it by the standard deviation, I remember that spread is, if I divide by a number, the measure of spread divides by that number also. So that's what's going on here. So if we go back to the problem here where Jenny got this 86 on her test, if we calculated the class mean was 80 and the standard deviation was 6.07, her z-score would have been about 1.99. So as I mentioned before, if I take every value in a normal distribution and calculated z-score, the resulting distribution is called a standard normal distribution. So that standard word there means a lot. It's going to tell you that the mean is always going to be 0 and the standard deviation is always going to be 1. Everybody okay there? So if I want to find the probability using a normal distribution, it's going to be akin to finding the area. So the way we want to do this is we're going to start by checking the distribution to make sure we're dealing with a normal distribution. And then we're going to write down the values of interest. What is the probability? Have to be greater than or less than or in between. We'll draw a picture of our normal curve and we'll shade in our area of interest. And we'll probably label the mean, the standard deviation, the boundary values. And then we'll perform a calculation. So we'll do a normal CDF, always CDF. And so the normal CDF, we give it a lower bound, an upper bound, a mean, and a standard deviation that'll output our probability for us. So let's look at an example. So if you have your calculator with you, I invite you to take it out to follow along. If you would like to follow along and you don't have a calculator with you, I have a stack up here you're welcome to borrow. So here we're told that z is related to the normal distribution 0, 1. So what kind of normal distribution is z if the mean is 0 and the standard deviation is 1? It's a standard normal distribution. So we'll start by sketching a picture of our curve. So here's our normal curve. I labeled the mean at 0, so that should match up with the peak. And then I labeled each tick mark one standard deviation. If the standard deviation is 1, we're just counting by ones. And then I shaded the area between -2 and +1. So far, so good. So on my calculator, I'm going to select normal CDF, so second, and then the distributions menu. I think that was the VARS button right below the down arrow. And I'll pick normal CDF. I'll list the upper as negative, or the lower as -2, the upper as +1, the mean at 0, and the standard deviation at 1. And plug that in, and I get about 0.819, or about 82%. Does that feel okay? What if I have the probability that z is less than 1? So again, start by drawing my picture. Notice here, since it's less than 1, I shade the entire thing out all the way. Everybody see that? Since it's less than 1, I shade the entire thing. So if I go to my calculator, how do I do, like, the lower is like -infinity. I can't put a -infinity into my calculator, so what I do is I just put the smallest number my calculator can handle, which is -1 times 10 to the 99th. That's the smallest number my calculator can handle. To get that scientific notation E, you press second and the comma is where that guy lives. And so we get about 84%. So far, so good. Here we have probability Z is greater than negative 1.5. Again, I'll draw my picture. So here's negative 1.5, and I'm going to shade everywhere to the right of that. So that's going to go all the way to positive infinity. So this time I'm going to do the upper as 1 times 10 to the 99. Again, that's my proxy for positive infinity. So if I grind that through on the calculator, I get about 93%. So, okay so far? If I have the probability that Z is less than 0, I don't even need my calculator to do this. How much of that curve is shaded? 50%, right? Boom, done. Everybody's okay with that? If I remember that the area under the curve is 1 and it's symmetric, so if I split it in half, 50%, done. Here's a tricky one. The probability that the absolute value of Z is greater than 0.8. So that's going to be that Z could be less than negative 0.8 or greater than positive 0.8. So what am I going to have to do here? 2 separate calculations, one for this part and one for that part. Everybody's okay with that? Yes. So you could do 1 and multiply it by 2? Absolutely. Or what I did here is I did the complement rule, where I found the white part, and I'm going to subtract it from 1. Also okay. Any of those methods that we've described would be okay, whether you do each piece separately and add them together, you do this piece and then multiply it by 2, or you do what I did here and find the white part and then subtract it from 1. Any of those would be acceptable. They'll all get you the same answer. So far, so good? Okay. So this is just going on and saying that if it's just a normal distribution, not a standard normal, everything works the exact same way. So consider this example where x is related to the normal distribution 10, 2 squared. So one way to do this is I could standardize my variable by making a z-score. But there's really no need to do that. Back when I was in school, well, in high school anyway, this is how you did every problem. You always standardized because we didn't have a calculator that could do this for us. So you had like a table and you had to look up, with the z-score on a table to figure out these problems. You had to do it all. There's like a table in the back of the book that you used to do this. It was a pretty big hassle. Your calculator can handle this. So if I wanted to do this as a z-score, I need to translate the bounds of my probability by calculating the z-score for each of these. So the probability that x is between 9.1 and 10.3 in the normal distribution 10-2 is equivalent to the probability that z is between negative 0.45 and positive 0.15 in a standard normal distribution. So this probability for this distribution is the same as this probability for a standard normal distribution. Or we can just kind of use our graphing calculator. So I'll start by sketching my picture. So here's my curve. 10 is the center. Each tick mark is 2 away. Right? Why are my tick marks 2 apart? Standard deviation is 10. How many tick marks should I include? Should always have 3 on either side of the mean. How did I know the mean was 10? Told me. Everybody's okay? All right. So using my calculator, lower is 9.1, upper is 10.3, the mean is 10, and the standard deviation is 2. Be careful when you write down our normal distribution, write it as mean comma variance, the standard deviation squared. You got to make sure when you enter it in your calculator, you're including the standard deviation, not the variance. It's a common mistake. So when we grind that through, we get about 23%. All right. Let's get into something that's a little less, like setup matters here a little bit because it's a story problem now. So eggs are laid by chicken, or eggs laid by chicken are known to have the mass normally distributed. With a mean of 55 grams and a standard deviation of 2.5 grams, what is the probability that an egg will weigh more than 59 grams? So if I sketch my curve, here's my mean at 55. Each tick mark is 2.5 away, so bloop, bloop, bloop. Drawn in 59 and shaded above it, so that's the part that we're looking for. So using my calculator, my lower is 59, my upper is positive infinity, mean is 55, standard deviation 2.5. Grind that through to get a just over 5%. What about the probability the egg is smaller than 53 grams? It's really the same problem, right? Sketch my picture, shade below, go to my calculator. This time we're going negative infinity up to 53. Same mean and standard deviation though. And here I get a just over 21%. How about an egg between 52 and 54? Again, sketch my picture. So we got that. Go to my calculator, 52 to 54. Bingo, bango, bongo. Just about 23%. Everybody feel okay? So what if I know the probability and I would like to recover the measurement? So if I know the probability that x is greater than x is, 59%, and I want to figure out what the value for x is, we're going to use a new operation here on our calculator. It's called inverse norm, where we enter the cumulative proportion, i.e. the percentage or the probability written as a decimal. Has to be written as a decimal with the mean and standard deviation. So say we have a normal distribution and we want to find out the measurement where z is less than a. If that probability is 87.7%. I don't know why I need to draw a picture. Basically, I just took this and tried to estimate where it looked like 87% of the area would be, and just drew it. To use my calculator, I'm using the inverse norm command. If you have your calculator with you, try this. Go to your distributions menu. So second, vars. You're looking for inverse norm. That's command 3. Enter the area, that's the probability. The mean and standard deviation are given to us with the distribution. And if we press enter, we get about 1.16. So far, so good. What if it's now z is greater than a is equal to 0.2? Inverse norm will only do less thans. How are we going to do this? We're going to write a complement. So that's what I did. So the probability that z is greater than a, if I take the complement of that, that's going to be the probability that z is less than or equal to a equals 1 minus 0.2. And I know the probability of z less than or equal to doesn't matter. So this is what we're going to look for. Is everybody okay with how I got to that new probability? So if I'm going to flip the inequality, I have to subtract my probability from 1. So if I do that, I get about 84%. Or I'm sorry, a is about 0.84, which looks like about my estimate, right? So far, so good. What if I want to find the measurement where z is between these two? Again, I'll try to draw a picture. So I just tried to guess about 42% of my curve was in between those two values. I can't do this directly. So what I'm going to do is I'm going to find the probability that I'm going to try to look for this one. And then subtract out that one. So if this is 0.42 for the whole thing, each of these two sections is 0.21, correct? So what I have then, if I want to do this whole section, this piece is 0.21. And then from 0 over, that's 50%, right? So that's going to be 0.7. That'll allow me to find the upper. Is everybody okay with that? So that's 0.553. And, oops. Because it's negative a to a, if I found positive a as 0.553, I know that's negative 0.553, right? Okay, so it says given that x is normal with a mean of 15, standard deviation of 3, determine x where the probability that x is less than x is 0.75. Again, I'll sketch a little picture. I don't need to necessarily get all my standard deviations in there. Just, I want this to look like about 75%. I just need to make sure it's on basically the correct side of the mean. Go to my calculator, 0.75, 15.3. Boom, about 17 should be my measurement for x, which seems like about right. Another example, cartons of juice are such that their volumes are given by the normal distribution 150, 5. 5% of the cartons are rejected for containing too little juice. Find the minimum volume to the nearest milliliter that a carton must contain if it is to be accepted. So I want So this is my picture for my 5% that are rejected for having too little juice. So let's find that. So 142 milliliters is the minimum volume. Everybody's okay with that? What would have been the issue if I would have tried to do, if I would have looked instead for like this section, the white section? Oops, I didn't mean to do that. If I wanted to look for the white section instead of this little piece over here. The white section to represent a greater than, like P of X greater than. And can I find that directly with inverse norm? I cannot. Inverse norm is only going to get you less thans. So I would have had to do a complement to it anyways, which is this. Right? If I look at this, if accepted, I'd be like, oh, it needs to be bigger than this. So I want 95. You know what I mean? But I can't do that side of it. I just wanted to take a minute because I think that reading it, that would have been my natural inclination. All right, I think I got, this might be my second to last example here. Sacks of potatoes with mean weight of 5 kilograms are packed by an automatic loader. In a test, it was found that 10% of bags were over 5.2 kilograms. Use this information to find the standard deviation of the potatoes. So this is a little tricky. So I know that my potatoes are normally distributed. I know their mean is 5, but I don't know the standard deviation. So what I'm asking for is, okay, well, I know that the probability that m is greater than 5.2 is 0.1. And I could use my inverse norm on our calculator to get that, but not without the standard deviation. So what do? I'm going to use a standard normal distribution. So I know that my z-score is going to be x minus mean over standard deviation. So that x minus mean is 0.2 over standard deviation. So if I do this, the probability that z in a standard normal, so z standard normal, of 0.2 over the standard deviation is 0.10. Or if I do the complement, that z is less than, this is 0.9. This I can figure out, because in a standard normal, do I know the mean? Yes, it's 0. Do I know the standard deviation? Yes, it's 1. So I do that. So that is the z-score when the standard normal is, the probability is 0.9 in a standard normal. I can then take that and set it equal to the 0.2 over standard deviation, do a little algebra, and get that the standard deviation is about 0.156. Bless you. This is probably the trickiest kind of problem you'll run into. So the trick is to convert or to find the z-score for the desired probability, and then use the z-score formula to solve for the standard deviation. That's it for me. That was my last example. I lied. Thought there was one more. Great googly moogly. What is going on with my screen?